Unit 6 is all about applications of integration. That's basically the last thing in Calculus AB, aside from, going back and filling in the blanks. So exponential growth and decay, we've actually seen a little bit before when we were separating differential equations. It's broken up into a couple of parts. So if you're going to be successful here, hopefully you can already solve separable differential equations. And to remind you what a differential equation is, if you're trying to decide if you can do that or not. A differential equation is something in the form dy dx equals some stuff. And to solve would be to separate variables, get the y's and dy's on the left, the x's, dx's on the right, integrate, and solve to get y on the left and a whole bunch of x stuff on the right. So we're going to use differential equations in context to solve applications, what, most students call word problems, which I find ridiculous. I think all problems have words in them, but whatever. We're also going to start writing statements of proportionality. We've done that a little bit, but they're going to be, this rate is proportional to that other thing. And we'll write a slightly different one in Newton's law of cooling, which is kind of part 2 of exponential growth and decay. So let's do a quick review and make sure you can separate variables, solve. So if dy dx is x squared y squared, we're going to solve for y, meaning get y by itself, not this y, with dy dx in there, but solving to find the function that has x squared y squared as its rate of change. Anyways, we're going to solve for y if y equals 1 when x equals 1. So the first thing I notice that you should notice is, I can divide both sides by y squared, and I can multiply both sides by dx to separate variables. So now we have y's and dy's on the left, x's and dx's on the right, and so we'll put an integral on both sides. Now, the right-hand side's pretty easy. The antiderivative of x squared with respect to x is x cubed over 3. And that's where we write our plus c. But the left-hand side, maybe you guys should have written this differently. If you haven't memorized yet that the antiderivative of 1 over y squared, or the antiderivative of 1 over x squared is negative 1 over y, or negative 1 over x, maybe you should have written that part as y to the negative 2 dy. Because then you can just think power rule. I'll add 1 to the exponent. That's going to be y to the negative 1. But I need a negative out front. So that's how we get negative 1 over y. Ideally, that's in your head, but you could have written it differently. Anyways, we are going to solve for y, but at a certain point, I want to get this constant filled in. So I might as well do that now, because I can just put in 1 for y and 1 for x. And negative 1 is 1/3 plus c, subtract 1/3, and that constant is negative 4/3. So I just find it easier to do that at the beginning when c is all by itself. Weirdly, unless we're doing exponential growth and decay, which we're doing today. Okay, so now I can put negative 4/3 where the c used to be, and I need to solve for this y. You can't just flip-flop numerator and denominator as things are written, because of this addition. So I think the easiest thing to do is multiply both sides by y, multiply both sides by 3, and then negative 3 is y times x cubed minus 4, and we'll just divide both sides by x cubed minus 4. I like having a positive, or what looks like positive overall, so I took that negative on the negative 3 and put it in the denominator, which gives us a positive 4 and a negative x cubed. All right, so if you did that, we can call that successful. You can solve separable differential equations. Okay. So when we're talking about exponential growth and decay, a lot of times we're talking about this situation. And it's not necessarily a population, because this could be the amount of material in a sample to do half-life or something like that. But let's just think population. The growth rate of a population over time is proportional to the size of the population. And so the growth rate of a population over time is proportional to the size of the population. So two things are being compared here. The two things are the growth rate, I don't know why we're not circling, and the size of the population. And what this is saying is, something that most people agree to be true just based on being alive for a while. If a population is larger, it has a tendency to grow more quickly. And if, let's say more babies per year. And if a population is smaller, it has a tendency to grow at a smaller rate. So that's all this is saying. But our job is to change this into really a differential equation, calculus looking stuff. So we're going to start off translating, well, not really translating, just rewriting the growth rate of a population. We'll translate that into calculus symbols in a moment, is proportional to. So how do we write is proportional to? Well, we use that K, constant of proportionality. And then how are we going to write the size of the population? Well, maybe a good placeholder would just be a capital P. And once we have size of the population as capital P, then we realize, growth rate of the population, that's the rate of change of this P over time. So we're going to change that to dP dt. So the growth rate of the population over time is proportional to the size of the population. So that's our differential equation that we're going to be using a ton. And by the way, this particular one, you're going to solve this exact differential equation a lot, which is good because you'll get really good at it. And my kids think it's pretty boring because you're doing the exact same thing, which I think that's a good thing. All right, deleted some marks that didn't need to be there from class time. Okay, so how are we going to solve? Well, we need to separate variables. Clearly, P is going to be divided on both sides, so we get dP over P. But what kind of thing is K? Well, K is constant. K is a number like 2, 3, 5, although rarely 2, 3, 5. Anyways, and what we're trying to get to when we're done is a population equation that has an input of time, like you put in 3 for 3 years, and it spits out the population. So because of that, we'll do dP over P, or 1 over P dP. And on the right-hand side, we'll just leave that K over there. We could have had K on the left, but that's just doing some algebra to undo it later. So then we're going to put integrals on both sides. The integral of 1 over P dP is the integral of K times dt. And then the antiderivative of 1 over P, well, that's natural log of the absolute value of P. But in this case, that P is standing for the size of a population, which always has to be positive, so we usually don't bother writing absolute value. The antiderivative of a constant dt is that constant times t. And just based on the way this went in class, let's just make sure we understand. What if I said, what's the integral of 2 with respect to x? That would be 2x plus a constant. What's the integral of 3 dt? That would be 3t plus a constant. What would the integral of 4 dr be? That would be 4r plus a constant. So when we say the integral of k dt, that k is a number like 2 or 3 or 4. Doesn't really matter what it is. That's just going to be kt. And don't forget your constant. Okay, so we want to get p equals. We need to get rid of this natural log. And so we're going to exponentiate. E to the power natural log of p, that's going to give us p. On the right-hand side, we're actually going to rearrange a little bit. E to the kt plus c, we can rewrite as e to the power c times e to the power kt. And that feels weird, but normally we do it in the other direction. If you're multiplying the same base, what do you do with the exponents? Well, you add them. So we're just breaking that apart. The reason we're breaking that apart is that e to the c has some meaning. So let's introduce a new symbol, p naught or p0, like the population at the beginning. So I'm going to say, when time equals 0, here's this new symbol, p0, which is supposed to represent the population at the beginning. We'll do this in context in a moment, and maybe it'll make more sense then. Anyways, so I'll replace the population with this new symbol for initial population. I haven't touched e to the c. And instead of k times t, well, we put 0 in there. But k times 0 is 0, and e to the power 0, well, that's 1. So what we end up with is initial population is the same thing as this entire block, e to the c. So what we end up with is, up here, you can think of we're replacing e to the c with initial population. And now you have an exponential growth or decay equation that you probably have used in other classes. The population is equal to the initial population, e to the kt. At least at our school, what do you do? E to the RT might be another way you see it. A equal, the population or the amount is equal to A e to the RT, P e to the RT, initial amount, e to some constant t. Okay, so if you think about what we just did, that's clearly calculus. We separated variables, integrated, and kind of rearranged. If this stuff comes up on the AP test, that's the calculus. If you do enough of these, you'll kind of realize, hey, we're always going to be jumping to this exponential growth and decay equation, but your job is to show what you know. And if it's a calculus test, your job is to show the calculus version. So the separating of variables and anti-differentiation is the only calculus. So don't skip over that and jump to the formula for exponential growth, unless it's multiple choice. In that case, definitely skip over things. All right, so we're going to basically do the same thing in context. The population of a hive of hornets is growing at a rate proportional to the size of the population. So the larger the population, the larger the growth rate. The smaller the population, the smaller growth rate. Okay, so this is exponential growth. On May 1st, the population was 10 hornets. 30 days later, there were 50 hornets. When will the population reach 125 hornets? So the first thing is, if the population is growing at a rate proportional to the population, that means the rate of change of population, dp dt, is proportional to the size of the population. So we'll start out with that differential equation. And even though we know where we're going, this is kind of the warning I just gave you, we're going to end up with the population is the initial population, e to the kt. Getting there is really what we need to practice. So here we go again. What do? We're going to separate variables. Divide p on both sides, multiply both sides by dt. So dp over p is k times dt, and then we'll put on some integrals. The integral of dp over p is equal to the integral of k times dt. The antiderivative of k with respect to t is kt. The antiderivative of 1 over p is natural log of the absolute value of p. But population of hornets is going to be positive, so we don't bother with absolute value. And don't forget your plus c over here on the right, just where it's out of the way. So even though this c is all on its own, we actually don't want to find it yet, because we don't want to find c. What we're going to do is find e to the c, like we did here. Okay. Anyways, so we need to get to p. We're going to raise both sides as powers of e. E to the natural log of p is going to be p. E to the kt plus c, well, that turns into e to the c, e to the kt. I'm going a little quicker because we're doing the exact same thing I did on the previous slide. Okay, so now this is a general solution of the differential equation. We want a specific one. Right now, we get it, I think. When will the population reach 125 hornets? Our answer is going to be a time when the population is 125 hornets. But if I put 125 in for the population right now, I get nothing useful. I need c and k. So what we're going to do is focus right here. On May 1st, the population was 10 hornets. And so obviously 10 is the population. What should we use as time? And the answer is 0. 0 is the easiest time because we get a nice simplification. K times 0, maybe we should write that. Let t equals 0 represent May 1st. And you might be thinking, well, what time on May 1st? Midnight? And the answer is, don't worry about that. We're rounding things off. We're trying to get some new skills, and we're not terribly worried about being super precise yet. We need skills before we do that. Anyways, so e to the power 0 is 1, and we get this entire e to the c structure is going to be replaced with 10 hornets. So we just slide that 10 in where e to the c used to be. Okay, now what? Can we put in 125 for population and get a time yet? No, we need this k. And so if I want k, that growth rate, that relative growth rate, what I'm going to need is a time and population pair other than the one I started with. And of course, that's right here. 30 days later, there were 50 hornets. So I'll put 30 in for the time, 50 in for the population, and now I can just do some algebra to find k. Well, how do I get to k? Well, I'm going to have to divide by 30 eventually. Before I do that, I'm going to have to take natural log of e to a power to get to that exponent. So first, I'll divide both sides by 10. Right? And then now you can see if we take natural log of the right-hand side, we'll get 30k, which means the left-hand side will have natural log of 5. Divide both sides by 30, and turns out k is natural log of 5 over 30. So now we finally have our specific solution to the differential equation. Population is the initial population, 10. E to the power of natural log of 5 over 30 times the time. So now we can put in 125 for the population, and we can solve for t. So just like before, we're going to divide by 10. We're going to take the natural log of both sides, and then we'll multiply. Instead of dividing, my brain just multiplies by the reciprocal, so multiplying by 30 over natural log of 5. If you put that into your calculator, you get 47.07970326. Now realize that's a great answer, or that's a great number, but it's not really an answer to the question, when will the population reach 125 hornets? And so what you have to realize is, oh, that's a time, that's 47 days. So the population will reach 125 hornets, and it doesn't say, you know, round to the nearest day or something like that, like the AP test normally does, so let's just leave the decimal in there. But realize, you know, it's already been 30 days since the simulation started, 30 days after May 1st. What does this 47 mean? Is that 47 days after the 30 days? Well, no, because we just defined the time as starting at May 1st. So this means 47 days after May 1st. We want to include that frame of reference. All right, so I think we're done there. All right, new problem. Use the fact that the world population was 2,560 million people, or 2.5 billion people in 1950, and 3,040 million people in 1960 to model the population of the world in the second half of the 20th century. We're going to assume that there it is. We're going to assume that the growth rate is proportional to the population size, right? So the rate of change of population is proportional to the population. Cool. What is the relative growth rate k? So I guess we have to find k separately. We would anyways, weird. And then we're going to use that model to estimate the world population in 1993, which is in the past, so that's a nice check, and to estimate the population in the year 2025, which is when I'm recording that, so I guess that's the present. Whatever. Okay, so after we have the rate of change of population with respect to time is proportional to the size of population, again, we're just going to separate variables. dp over p is k times dt. Integrate both sides. The integral of dp over p is equal to the integral of k times dt. And find antiderivatives. Antiderivative, well, let's go back. Antiderivative of 1 over p is natural log of p. We can drop the absolute value. The integral of k with respect to t is kt, and we definitely need a plus c. Okay. Well, we need to find k, and first, let's get population on its own. So e to the power of natural log of p is equal to e to the power of kt plus c. And so population is e to the c, e to the kt. And again, we know that this e to the c, or at least I do, hopefully you do, e to the c, that's going to be the initial amount. But kind of weirdly, it doesn't matter whether you pick 1950 to be the beginning, 1960 to be the beginning. Heck, you could choose 1993 to be time equals 0. most people think it makes most sense to go like chronologically. So we'll just choose 0 to be 1950, which means I'm going to say, oh, well, 3,040 million, that's time equals 10. And 1993, that's time equals 43. Okay, so now we'll substitute in 2,560 million is e to the c times e to the 0. E to the 0 is 1, so we replace e to the c with that 2,560. It does say we want the relative growth rate, so we need a time population pair, and that's, of course, this 3,040 million in 1960. But remember, we're using time equals 10 because 0 is 1950, so 10 years later is, well, 10. There you go. What I'm hoping is you can do this algebra in your head. We're going to use a calculator eventually anyway, so don't worry about simplifying. So I'm going to divide both sides by 2,560, and then I'm going to take natural log of both sides, and then I'm going to divide by 10. So natural log of 3,040 divided by 2,560, all divided by 10. So there's our k, our relative growth rate. And with that, we can write our population equation. 2,560, the initial amount, e to that k we just found, natural log of 3,040 over 2,560, divided by 10, all times t. So when time equals 43, remember that's 1993, we just put the t in, and that's clearly a calculator thing. So in 1993, you don't want to say there were. It's like the model predicted that there would have been 5,359,996,271 people, which of course is kind of ridiculous that we're pretending, it's down to the nearest person. But it's a model, it's probably pretty close. You can look up those statistics if you want. I'm not going to bother putting in 75 for 2025 because that's the same sort of thing, but you may want to see how close we are to the 8 billion I heard on the news recently. Okay, last example is half-life. So hopefully you understand half-life a little bit. If you don't, here you go. So radioactive material, if you just leave it sitting there, is going to decay. It's going to break down into other parts. Now, you're going to see in a moment, we have a 100 milligram sample. Now, by the way, I'm not a chemistry teacher, so I'm just going to do my version, and hopefully it's close enough. Anyways, so each particular atom has some non-zero chance of decomposing into other stuff. Okay, so any one particular atom at any time might decompose, but it's pretty unlikely. However, if you have a whole bunch of them together, and if you know how much a milligram is compared to a mole, that's actually a lot. So if you have 100 milligrams, the chance that one out of those billions, trillions, quadrillions, who knows how many, of atoms is going to decay is actually reasonably high. Okay, so radium decays at a rate proportional to the amount present in a sample. I'm trying to explain that idea. Now, the part we're going to use right now is the fact that the half-life of radium is 1,590 years. So what that means is, if we wait long enough, I guess theoretically, because we can't wait that long and actually test it out, a whole bunch has decayed into other stuff, and instead of 100 milligrams, there are 50 milligrams left. Okay, so that kind of makes sense. What didn't make sense to me, that I think I understand now, but I might be wrong, is each of those atoms in the 50 milligram sample has the same likelihood as each of the atoms in the 100 milligram sample to decompose, right? But the fact is there are less of them. So the likelihood that one out of the 50 milligram sample or one out of the 100 milligram sample would decompose, well, out of the 50 milligram sample, that probability is less because there are just half as many atoms. And so the weird part, the thing that high school me didn't understand is, I thought if we waited another 1,590 years, or whatever example Dr. Scott gave to me, that was my chemistry teacher, well, the rest would decay. 50 milligrams went away, so another 50. No, because there were less atoms, the likelihood that any of them would decompose is less, so we actually just end up with half of what was left. Okay, so hopefully that kind of makes sense to you now. Hopefully I didn't screw that up too badly. So a sample of radium-226 has a mass of 100 milligrams. We'll call that the initial amount. Find the formula for the mass of radium-226 that remains after 88 years. Oh, why did I say 88? Sorry, that must be an isotope. Again, I don't know chemistry. That remains after T years. And so we go back to the fact that radium decays at a rate proportional to the amount. As in, because comparing 100 to 50 to 25 grams, there's less stuff in there, the likelihood that any of it decomposes gets lower and lower and lower. So we're going to start out with the rate of change of the amount, dA dt, is proportional to the amount present. Now, I realize I'm not doing something that math people would do, because again, I'm whatever you want to call me, a high school math teacher. Everybody else says, that should be a negative K because it's a decomposing. And to that I answer, yeah, but isn't K just going to turn out to be negative anyways? And so, I don't know, that's the way I do it. Anyways, so we're going to separate variables. dA over A is K times dt. And then we're going to integrate both sides. The integral of dA over A is the integral of K times dt. And this is the same thing we've done, just A's instead of P's, so whatever. Antiderivative of 1 over A is natural log of A. The amount is always positive. And the antiderivative of K with respect to T is KT, don't forget plus C. And just like before, we want a formula for the amount present. So e to the power, and we get the amount, oh, dang, that's still going out of order. I thought I fixed that animation. Okay, so we should have the amount is equal to e to the c, e to the kt. There we go. So then we want to fill in this e to the c, and we know it's going to be just the initial amount, this 100. And so I guess we're just going to say time is 0, corresponds to the amount of 100. 100 is e to the c times e to the 0. So 100 is e to the c, and we have the amount is the initial 100, e to the kt. Now, we're getting closer, but this is still not quite the formula for the mass that remains after t years. We need this growth rate here, so we need an amount and a time, which I think confuses people a little unless you understand that this 1,590 years, that actually tells you the time, and it implies an amount. If we start out with 100, and we wait one full half-life, 1,590 years, how much is going to be left? 50. Okay, so now we need to solve for k, so we'll divide by 100, so 50 over 100 is a half. We'll take the natural log of both sides to get rid of this e, and then we'll divide by 1,590. Cool. Oh, man. All right, background removed. So we get the amount is the initial 100, e to that k we just found, natural log of 1/2 over 1590 times time. All right, so there is our formula. So there it popped up. I don't know if you noticed in blue. I can't handle Microsoft PowerPoint. Okay, so how would we find the mass after 1,000 years? That's pretty trivial here. We're just going to put in 1,000 for time and grab a calculator. Now, how much is that going to be approximately? You should be able to estimate. Well, if we start out with 100 milligrams, 1,000 years is not all the way to a half-life, so it's going to be definitely more than 50, less than 100, and probably less than 75. This is a nonlinear relationship, but 60, 70, that's a good guess. And turns out to be 64. But that's just calculator stuff. How would you figure out when the mass is going to be reduced to 30? Well, of course, we're going to put 30 in for the amount and, use some algebra, do a calculator thing. But we can estimate that too. After 1,590 years, 100 milligrams would be 50. After another 1,590 years, so what is that? 3,180 years, we'd be down to 25 milligrams. So it's going to be pretty close. So we just put in a 30, rearrange, and turns out it's 2,850 or something like that. Doesn't really matter the number. All right, I hope that helps.